Assalamu alaikum students. Today's our topic is going to be about numericals of the chapter oscillation. Let us read the first numerical. A force of 0.4 Newton is required to displace a body attached to a spring through 0.1 meters from its mean position. Calculate the spring constant and our answer should come 4 Newton per meter. Now the data which is given to us is the force is given to us which is 0.4 newtons. The displacement which is given to us is 0.1 and we have to calculate the spring constant. So we have the formula of Hooke's law that F is equal to minus kx. Now as we know the formula F is equal to minus kx, but here we are not going to use the negative sign because k is a constant value, that means spring constant. So it is in constant value or no direction value. So that is why there is no negative sign over here. That is why f over x will have 0.4 Newton force divided by 0.1 displacement, which has the value now of 4 Newton per meter, which is a spring constant K. In a similar way, in question number 2, it says a pendulum keeps a perfect time at a location. The acceleration due to gravity is 9.8 meter per second exactly. When the clock is moved to a higher altitude, it loses 80 seconds per day. Find the value of g at this location. And our answer should come 9.78 meter per second square. Now, in this case, let us first understand what he's talking about. Here's a grandfather clock, as you can see over here, and there's a pendulum underneath it. Now, if we see that as the pendulum basically moves to and fro, the movement from here to here, it takes 1 second. And when it moves back, again, it takes 1 second. So the total time for this pendulum to basically complete is one vibration is 2 seconds. That is a time period. So this clock is representing a seconds pendulum. A seconds pendulum is that pendulum which requires 2 seconds to complete its whole vibration. Now, if we move it to an higher altitude, let's say on the top of a mountain, then what will be the value of G at this new location? Let me clear that out. What will be the value of G in this new location? Now, in this case, the data which is given to us is the time period of a simple pendulum or seconds pendulum, as we know, is 2 seconds. The cycles per day, that means we have a day contains basically 24 hours, and in those 24 hours there is 60 minutes, and in each hour there is 60 minutes, and in each minute there is 60 seconds. So when we multiply these all of these, it will be 86400 seconds in a day. Now as we know that it is a seconds pendulum, so it doesn't basically complete 84600 basically intervals, or you can say vibration. It completely half of that because it requires 2 seconds to complete its whole vibration. So for one vibration for one side, we are taking it uh, as a loss in this case, so we are dividing it by 2 in this case, and that is why our answer is 43200 cycles per day. Similarly, in the ground level, we have the value of G, which is equal to 9.8 meter per second square. So that as the question tells us that it is 80 seconds per day, which is lost. So the time lost in a day is 80 seconds. So what do we do? Cycles per second is n, let's say, and we have already calculated that. Now, because 80 seconds was for the whole day and for 86400 seconds, so we have to half that, because how many vibration will be there? in a whole day, it will be half of that. So that is why 4300, 43200, we subtracted 4 basically from it, 40 from it, so that we have a vibration for a one-sided movement of the pendulum. And what do we get? The cycle per day, we get 43160, and that is the cycle or vibration you can say per day. Now, the time period for this new vibration, what is going to be the time period? We can calculate it by dividing the total time in one day by the number of cycles per day. That means the new time period is now going to be the total time, which is 86400 divided by the cycles per day, which is 43160. So our new time is going to be 2.001 seconds. So as we can see, the time period has increased. The gravitational acceleration, which is new over here, which we have to calculate over here, value of g, the new g, now we can calculate it very much easily by using this formula of time period of a simple pendulum, which says t is equal to 2 pi under root L over g, where L is the length of the pendulum and g is the gravitational acceleration. Now we have to basically find out the value of g. So taking square on both sides, so it will be t square is equal to 4 pi square L divided by g. So what do we do from here? We take g on one side, which is the gravitational acceleration, and take all the other quantities on the other side. It will be 4 pi square into L over t square. And similarly for the new value of g, it will be g new is equal to 4 pi square divided by t square, or you can say t new. Actually, this is a new time period which we have to use in equation number 2. So when we divide these two, what do we get? Dividing equation 2 by equation 1. So what we have done is g new is equal to, as we know, 4 pi square L divided by, let me clear that out for you. So it is L divided by t square, which is new, divided by, we have to divide it by equation number 1. So g divided by 4 pi square L divided by t square. So this 4 pi and this 4 pi basically cancels out, and this L and this L cancels out. So what we are left with? We are left with g new divided by g is equal to 1 over t square new divided by 1 over t. So this t goes on to top, and that is why the new formula which we have now is g new over g is equal to t square divided by t new square. Now, if we want to calculate the value of g, which is new, we take the g to the other side. Over here, it is basically dividing. On the other side, it will multiply. So it will be g new is equal to g into t square divided by t new square. Putting in the values, what do we get? G new is equal to 9.8 into 2 square divided by the new time, which is 2.00, right over here, which we calculated. We are putting in the values of square. So 2.001 square, which is new. So our new value of g is going to be 9.78 meter per second square, which is the value of g right here, 9.78 meter per second square. And that is our answer. If we continue to question number 3, it says calculate the length of a second pendulum having a time period of 2 seconds at plate where g is 9.8 meter per second square. So here approximate length is given, which is 0.992 meters. So we have to find it out. Now for the data part, as we know, it is second pendulum. So the value of time period is 2 seconds, and the value of g is 9.8 meter per second square. That is the given data to us, and we have to find the length of the pendulum. First of all, we have to understand the formula of the simple pendulum, which is according to the time period, t is equal to 2 pi under root L by g. Now, if we have the same formula over here, t is equal to 2 pi under root L over g. So taking square on both sides because we want to find the value of L. So it will be t square is equal to 4 pi square. No, this is square into L over g. And when we find out the value of L will be equal to g t square divided by 4 pi square. So putting in the values of all the quantities, it will be L is equal to 9.8, which is the value of g, 2, which is the value of t square, divided by 4 into 3.14 whole square, pi has the value of 3.14. So after solving this, what do we get the value of L? L will be equal to 0.992 meters. So if we round it off, it will be equal to 1 meter approximately. Now, as we can see in the next question, let's say a body of mass M suspended from a spring with a force constant K vibrates F1 when its length is cut into half. The same body is suspended from one of the half frequency F2. Find out F1 divided by F2, and its answer should be 0.707. Now, this is a situation that we are considering, that there is a spring over here and there's a mass attached to that spring. Let's call that mass M, and it has a length, let's say, of x1, and it is vibrating or with a frequency up and down with f1. Now he says that if we basically cut that spring into half with the same mass attached to it, and now the distance of that spring is, let's say, x2, which is half of x1. So the frequency over here will be f2, and we are required to find out the comparison between f1 and f2. This is the requirement over here. Now, let us see how it is done. We have the mass. We don't care about the mass because the mass is now irrelevant, because we are not concerned with the mass. We are concerned with the distance and frequency only. So the spring constant is given k to us. The frequency of a complete spring is given is f1, which we have mentioned over here. The displacement of a complete spring, which is x1, which is mentioned over here. The frequency of the half spring, which is f2, which is mentioned over here, and the displacement of the spring, which is x2, which is mentioned right over here. And we have to find out f1 divided by f2. So for that, we have to find the frequency. What is the formula for frequency? For that, we have to understand the formula of time period. Time period is equal to 2 pi under root L over G. So as we know that frequency is the inverse of time period, putting that value of time period in this equation, what do we get? 2 pi under root L over G, or we can say that 1 over 2 pi under root G over L. It's the same thing, just the values of G and L are interchanged now. Now let's see that what is the formula which is given right over here. Yes, for a mass spring system, the frequency formula is given by 1 over 2 pi k over m, and basically that was a formula of a pendulum. Now we have to discuss the formula of a mass attached to a spring system. So F is equal to 2 pi k over m. So again, if we have the time period of a simple mass attached to a spring system, it will be 2 pi under root m over k. So similarly, F will be equal to 1 over T. It will be 1 over 2 pi K over M. You can say it like that, or you can say in this way that 2 pi under root M over K. It's the same thing. So this is the way we have gotten this formula. The concept has to be like this. Now in this case, we have the frequency in this case. Now the formula of a frequency, which we attained through the formula of time period. And now we are going to find out the value of k as well. Now, as we know from Hooke's law that F is equal to kx. And from that, we basically figured out that k is equal to f over x. Now, as the body was under the action of gravity, so F will basically represent as weight. So F will be equal to mg divided by x. Now, putting this value in the formula which we have of the frequency, which was F is equal to 2 pi under root m over k, or we can say F is equal to 2 pi under root k over m if we multiply it. So we're putting the value of this k which we have found out in this formula. Let's see how it is done. Now F, we know that F is equal to 1 over 2 under root mg divided by mx. So we are putting the values of this value of k in the formula of frequency. So this m and this m will cancel out. What is left behind? It will be F is equal to 1 over 2 pi into under root L over G over X. Now, in this case, the frequency of one complete spring, for the first spring, which we can say, it is F1. F1 will equal to 1 over 2, the value of G will remain the same, divided by the displacement of the mass attached to a spring system, it will be X1. So let's call this equation number 1. Similarly, if we basically apply the same concept to equation 2, or we can say the second part of the mass attached to a spring system, when spring is cut into equal parts of the same mass suspended with the half spring, then the frequency of the half spring is, it will be F2 is equal to 1 over 2 into under root G over X2. Now, as we know that X2 is basically half of X1. So put this value of X2 in this equation. What do we get? We get F2 is equal to 1 over 2 under root G over X1 divided by X2. So we just replace it. So this 2 will go on to top and multiply with G. So it will be equal to F2 is equal to 1 over 2 pi under root 2G into or divided by 1 X1. Now we can compare this equation, equation number 1, and this equation. But first, let us take common this 2 over here. If we take 2 under 2 common from this equation, what do we get? We get F2 is equal to under 2, which is taken common, divided by or multiply by, instead in this case, 1 over 2 into under root G over X1. So 2 under root 2 has been taken common. But what is this equation? Isn't this the equal to F1? So we're putting this value of F1 over here. So what do we get? Putting values of equation number 2, oh sorry, equation number 1 in equation number 2. So if we put it, what do we get? F2 will be equal to under root 2 into F1. And if we rearrange this equation, it will be F1 divided by F2, which was a comparison. So it will be 1 over under root 2. So if we calculate in our calculator, it will be F1 divided by F2 is equal to 0.707. And that is our required answer. And there is no unit because it is a comparison between two frequencies. Let's move on to question number 5. A mass at the end of a spring described as SHM and t is equal to 0.4 seconds. Find out A, that means acceleration, when the displacement is 0.04 meters. And the acceleration should be minus 9.86 meters approximately. Now, in this case, what data is given to us, the displacement is given to us, the time period is given to us, the acceleration we have to find. Now, if we have the formula, let's consider the formula for SHM because this is the key word over here. The required formula for SHM, that acceleration was directly proportional to the displacement, but with opposite direction, and there was a constant over here, which is omega, if you put equal to sign over here. So in this case, we have the acceleration, we have the displacement, and we can calculate the time period by using this omega as well. Now for this tricky part, we have the formula, which is equal to A is equal to minus omega square x. Now, as we know that omega is equal to 2 pi divided by t. So putting this value of omega in this equation, what do we get? It will be A is equal to minus 2 pi and divided by t whole square. Now we have the value of t, x, and now we can find out the value of A as well. So A will be equal to minus 4 pi square divided by t square into x. Putting values, what do we get? It will be minus 4 into 3.14 square into 0.04 divided by 0.4 square. So what is our answer? Our answer is minus 9.8 meter per second square, which is our required answer as well. A block weighing 4 kilograms extends by a spring by 0.616 meters from its unstretched position. The block is removed and 0.50 kilograms body is hung from the same spring. If the spring is now stretched and then released, what is the time period of the vibration? Now, let us understand the situation first, that when we attach a mass attached to a spring system over here, and there is 4 kilograms right over here. Then the spring is basically stretched to 0.16 meters. So if we keep the same spring right over here, but we change the mass only, so he's saying that after changing the mass right over here, instead of 4 kilogram, we are putting 0.5 kilogram. What will be the time period in that case? So we have to calculate the time period. So first of all, we have the mass of the block from which we can basically, and we have the extension as well, from which we can calculate the spring constant. If we have the spring constant, then we can easily calculate the time period. Let's see. To find, we have to find the spring constant K. As B part, we have to find the value of time period T when it is 0.5 kilograms hung by the mass attached to a spring system. So first of all, for the mass attached to a spring system, we have to find the value of K from Hooke's law, which is F is equal to Kx. We can find out the value of K. So K will be equal to F over X. Putting values of F, which is equal to W or weight of that mass attached to a spring system, it will be equal to mg. So putting values of that mg in the equation, it will be k is equal to mg divided by x. So mass which is given to us is 4 kilograms, the value of g is 9.8, and the displacement which was given was 0.16 meters. Now in the next case, we have the value of k, which is 245 Newton per meter. Now we have to calculate the time period as well. Now, if we remember the formula of a mass attached to a spring system, that T is equal to 2 pi under root m over k. Now we have the mass, which is 0.5. We have the value of k because the spring wasn't changed in this whole procedure. So spring constant will remain the same. So that is the formula which we are going to use. T is equal to 2 pi under root m over k. Putting in the values, it will be 2 multiplied by 3.14 into under root 0.5 divided by 245. So value of t will be 0.28 seconds. Question number 7 says, what should be the length of a simple pendulum whose time period is 1 second? What is its frequency? So very interesting question, that the time period is given to us, which is 1 second now. And the value of g is also given to us, which is 9.8 meter per second. And we have to find the length of that pendulum, and we have to find the frequency at that pendulum as well. So in this case, first of all, let us find the length, which by this formula t is equal to 2 pi under L over g, taking square on both sides to find out the value of L. It will be t square is equal to 4 pi square into L divided by g. So take the all the quantities on one side and L on one side. It will be L is equal to gt square divided by 4 pi square. Putting in the values, we get g value is 9.8. The value of t was 1 second square divided by 4 into 3.14 whole square. So the value of length of the pendulum is 0.25. Now for the frequency part. So as we know that frequency is the inverse or reciprocal of time period. So time period is 1 second. So 1 divided by t, or we can say 1 divided by 1 is equal to 1 hertz, and that is the required answer. But it is CPS. What does CPS means? It means cycles per second, which is another form of saying frequency, or we can say hertz in this case. Question number 8. A spring whose spring constant is 80 Newton per meter. So it is -1 over here, vertically supports a mass of 1.0 kilograms at rest position. Find the distance by which the mass must be pulled down so that on being released, it may pass mean position with a velocity of 1 meter per second. Now over here, the tricky part, 1 meter per second is the velocity over here. So 1 meter per second is the velocity. And the key point over here is the mean position. Now the K constant is also given to us, which is 80 Newton per meter, and the mass is also given to us. So this is the data which is given to us. Spring constant, which is 80 Newton per meter, and we have the value of mass, which is 1 kilogram, maximum velocity, which is 1 meter per second, and we have to find the maximum displacement, which is x naught. Now for this, we have to understand the situation first, that here is the mass attached to a spring system vertically, and we are stretching it, and we stretch it so that when it comes back to its mean position, let's say over here, it has a velocity at this position which is 1 meter per second. Now, how much will be the distance at this case, this x naught, which we have to find out. Now, if we remember the formula of velocity in a circular motion and the simple harmonic motion, it will be v naught is equal to omega under root x naught square, we can say r square minus x square in this case. Now, in this case, as we know, it is mean position, so the value of x will be equal to 0. So v naught is equal to omega x naught square minus 0, or we can say v naught is equal to omega x square naught, sorry, x naught square, and this x square and this under root basically cancel out. It will be v naught in is equal to omega x naught. Now we know that omega is equal to under root k over m. So let us put this value of omega in this equation. So what do we get? V is equal to, or v naught is equal to under root k over m into x naught. So this is the formula which we are required because we want to find out the value of x, and k constant is given right over here, which is 80. The mass is given, which is 1 kilogram, and velocity is also given, which is 1 meter per second square. So let us solve this equation now. We have the formula that v naught is equal to x naught under root k over m. Let us put in the values. It will be 1 is equal to x naught, which is 1 is the velocity of the v, and the value of k was 80 divided by 1, which was the mass under root. So it will be equal to 1 is equal to x naught into 8.944. Taking 8.944 to other side, it will be x naught is equal to 1 divided by 8.944, and our answer will be 0.11 meters, and that is the place where the velocity will be equal to 1 meter per second. Question number 9 says 8,000 gram body vibrates simple harmonic motion with the amplitude of 0.3 meters. The restoring force is 60 newtons and the displacement is 0.3 meters. Find out time period, acceleration, velocity, and kinetic energy and potential energy as well. When the displacement is 12 centimeters, so our answer should be 1.3, acceleration should be 3 meter per second square, the velocity should be 1.4 meter per second, the kinetic energy should be 7.6 joules, and the potential energy should be 1.44 joules. Now for the first case, we have the mass of the body, which is 8 kilograms. We have converted the grams into kilograms. Amplitude is basically 30 centimeter, you can say 0.3 meters. The restoring force which is given to us is 60 newtons. And the displacement which is given to us is 30 centimeter or 0.3 meters. To find, we have the time period we have to find the acceleration, speed, kinetic energy, potential energy. And when the displacement is x, we have to find it. Then what happens at that position? So for the first part, the time period. So for the time period, we have to understand the Hooke's law and we have to find the value of k from that formula, that we know that F is equal to k x naught, and we know that k is equal to F over x naught. So putting the values of F, which is equal to 60 Newton divided by 0.3. So the value of k is equal to 200 Newton per meter. Now we have the value of k and then we can calculate the time period, which is by the formula. Using the formula for time period, which is t is equal to 2 pi under root m over k, right over here. Now we have all the values and we can put in this formula. What do we get? It will be values of m, which is 8 kilograms, values of k, which is 200, the value of pi, which is 3.14, right over here, and 2 will be written as it is. After solving this, the value of t, it will be equal to 6.28 into 0.04. After solving this, it will be 0.04. And when we multiply it, it will be 6.28 into 0.2. So time period is approximately equal to 1.256, or we round it off, it will be 1.3 seconds, and that is our required answer for time period. Now for the second part, the acceleration part. Now acceleration, as you know that it is given in the simple harmonic motion, is a is equal to minus omega square into x, where omega is equal to k over m. Now in this case, if we put the value of omega in this equation, it will be a is equal to minus k over m into x, and we have the value of k as well as of m and x. So putting in the values, what do we get? It will get minus 200 divided by 8 into 0.12. Now the acceleration which is given to us is 3.0 meter per second square, where the negative sign is showing that it is towards the mean position, which is the necessary condition for the simple harmonic motion. The negative sign shows the acceleration is directed towards the mean position. The speed part now. The speed of the body executing a system is given by the formula that v is equal to omega into under root x naught square minus x square, or we can say r square minus x square if we are taking the radius in this case. Now in this case, as we know that omega is equal to under root k over m, so it will be v is equal to under root k over m, and we know the value of omega, which is under root k over m. So putting the values over here, what we get, v is equal to under root 200 divided by 8 into under root 0.3, which is the maximum displacement, square minus 0.12 whole square, which was a distance given to us in the question. So after putting the values, it will be v is equal to 5 into under root 0.09 minus 0.0144. Velocity, which will be given to us, will be equal to 5 into under root 0.0756. Velocity, approximately, it will be equal to 1.37 meters. Or if we round it off, it will be 1.4, but we'll still take 1.37 meters. Now for the kinetic energy, as we know the formula for kinetic energy, it is 1 over 2 mv square, and we have the value of velocity now. So putting in the value of velocity, which was approximately 1.37 square, value of mass, which is also given to us, which is 8 kilograms, putting in the values before multiplied by 1.89. So kinetic energy which is given to us is a 7.56, or rounding it off to be 7.6 joule. And in a similar way, we can figure out the value of potential energy by using the formula, which is equal to half kx square. We have the value of k, which is 200, and the value of x is 0.12 square. So putting in the values, what do we get? It will be 100 multiplied by 0.0144. So potential energy is equal to 1.44 joules right over here. Now, in this question, it says find the amplitude, frequency, time period, and object oscillation at end of a spring. If the equation, if position at instance given by x is equal to 0.25 cos pi by 8 into t, find the displacement also object after 2 seconds, and this is the given data to us. So this formula is very much important. I mean, basically remember the formula of displacement, which is x is equal to x naught cos theta. This was the generalized formula which we have tried before. X is equal to x naught, where x is the instantaneous displacement and x naught is the amplitude which we are considering, and theta is basically the phase in which the displacement is at that moment. So let us find the formula. We have the equation, which is x equal to 0.25 cos pi by 8 into t. So in general form of equation, it is x is equal to x naught cos theta. Now, if we compare these two equations, x is x, x naught is 0.25, cos is cos, and theta will be equal to pi by 8 into t. And as we know, theta is equal to omega t. If we compare that also, we can find out the value of omega and frequency as well. So first of all, we must basically compare these two equations to find the value of amplitude. So comparing 1 and 2 from the above equation, it will be the maximum amplitude is going to be 0.25 meters. Now for the frequency part. The frequency part, basically, we are considering theta is equal to 2 pi under root t, or if we compare it with this equation, theta is equal to omega t. So if we compare t is t and theta is theta, so omega will be equal to pi by 8. And we know that omega is also equal to 2 pi t, or we can say omega is equal to 2 pi, because this is the reciprocal of time period f. So we are comparing this equation with the pi by 8. So in this case, comparing equation 1 and equation 2, what do you get? Omega is equal to pi by 8, and as we know that omega is equal to 2 pi f, as we know that, we are comparing the values, so pi will be cancelled over here, 2 will go on to the side, it will multiply with 8, it will be 1 over 2 multiplied by 8, or we can say 1 divided by 16 hertz. Now this is the frequency which we have calculated. We can also simply calculate the time period, as we know the frequency is the inverse of the time period, and it will be 1 over 1 over 16. So 16 will go on the top, and basically the time period in that case, if we have to calculate the time period in opposite case, if we have to calculate the time period in that case, so frequency is given to us, it is 1 over 16, 16 will go up, it will be, time period will be equal to 16 seconds. Let's see how it is done. So time period is basically the inverse of frequency, so time period will be equal to 1 divided by 16. 16 will go up, it will be t is equal to 16 seconds. Now for the displacement part, for 2 seconds, what will be the displacement at 2 seconds? So putting the value of 2 in the above equation, what do we get? We get x equal to 0.25 cos theta, and in value of t we are putting in the value of 2, so it will be 0.25 cos pi by 8 into 2, and when this 2 cancels with this 8, it will be pi by 4, so it will be x equal to 0.25 cos pi by 4, or we can say, instead of writing down in radian form, we can say cos 45. So x is equal to 2.5, sorry, 0.25 cos 45, and when we put in the value of cos 45, it is going to be 0.707 multiplied by 0.25. When we multiply it, we get 0.176, or we round it off it to be x is equal to 0.18 meters, and that is our required answer as well. I hope you enjoyed today's lecture. Inshallah, we'll meet again. Allah Hafiz. Bye bye.